Hello, this is Dr. Asan Abdullah with the course Introduction to Natural Language Processing, and we are at lecture 3B. Basically, we are looking at text modeling. So, what is text modeling? Text modeling is representing the text as numbers, representing sentences as numbers, documents as numbers, not a single number but a collection of numbers so that we can perform all the mathematical and statistical operations on those numbers. So, there is the bag of word models and then there is the vector space model. So, we go over to the supplemental website, the address is on your screen. So this course consists of 15 topics, and the topic which we are covering is the text modeling, bag of word models, and the vector space model. So this course basically uses the supplemental learning management system, which has some excellent features, which you will find very useful in your comprehension, in your progress, successful progress in this course. So now we move on to the supporting website. As you can see, there are quite a few courses here, core computer science courses and other cutting edge courses with latest content. It's not outdated, it's latest content. References are also given with everything. So we move on to the course of our interest, which is natural language processing. And the topic of our interest is the bag of words model, which we have covered. So what I'll do is I'll skip over the bag of words model and I go over to the vector space model. So what is the vector space model and how it is built? So in the vector space model, we basically create the vocabulary term list, which we did in the bag of word model. As a matter of fact, the bag of word model is a special case of the vector space model, and represent documents as a vector, which is like a one-dimensional array, and weighing the terms. Now this is the something which is different from the bag of words model, that importance is associated with the terms in the documents, and the documents are represented in terms of the importance of the terms. So then are the similarity measures. As a matter of fact, I've only mentioned two, but there are many more, Jaccard coefficient also. So what those similarity measures do is that what we have these term vectors. So using those term vectors and identifying which documents are similar to which documents. So example is, say we have a corpus which we discussed. So I love programming, and you can read it. So we create this vector space, for example, and the corpus may contain cat, dog, and apple, and whatever. So what we do something called the term frequency and inverse document frequency. So term frequency is simple, that how many times a term occurs, and the inverse document frequency basically in plain English means that the words which don't occur very frequently, like stop words don't have much value because they occur very frequently. So the words which occur infrequently, they have the more information content. So basically we end up multiplying the term frequency with the inverse document frequency. So the example which we be considering, other than the one which I mentioned here. So based upon that example, the different frequency of the words and their occurrences, and of course if you look at that particular example, I love programming is fun, and so on. So these are the vectors. These are the three vectors for the three documents. These are the documents. So in the next slide I will be doing these calculations also, but if you look in the feature space, so we have these term 1 or the document 1, 2 and 3. So these basically vectors point to a multi-dimensional space. Of course it's not possible to show you 1, 2, 3, 4, 5 and 6 dimensional space. So we are restricting ourselves to only 3 dimensional space. That is documents with 3 terms. Okay, all right, because 3 terms means because this sentence will have, this is the 3 dimensional space, so x, y and z. So how different components in the vector space model are assigned a weight, which I promised I'll explain to you. So we have this T of W. T of W is the number of times the word W appears in the documents divided by the total number of words in the document. Okay, that is one. Then is the inverse document frequency, log of total number of documents divided by the number of documents containing the word W. And so this is basically very simple. And of course we are assigning the binary weights with binary values 0 and 1. It occurs or it does not occurs. So I'll go into more detail and it will become very concrete. Before we do that, let's briefly look at the different metrics for measuring the similarity. So cosine similarity takes the cosine of the angle between the vector in the multidimensional space. The Euclidean distance measure the Euclidean distance between those vectors. Jaccard similarity, Pearson correlation is very powerful, and Manhattan distance based upon the streets and the blocks. So these are explained here. So let me briefly let me zoom this. Okay, so I have these vectors. So the cosine similarity is, this is how the cosine similarity is calculated. This is the dot product, right? And then I have the Euclidean distance. Euclidean distance is the difference of the squares of the sums, their under root. So that's the Euclidean distance. Jaccard similarity is based upon the set approach, and Pearson correlation is based upon the means, and it's very powerful. And then is the Manhattan distance, that how much you can move around. And one thing more, I may not have explained Manhattan distance a lot in this slide, but if you go to the main page of this course of this tool, and in the yellow box you type Manhattan distance, then of course you can get more concrete examples about the Manhattan distance. So that is the beauty of this tool, that you can search across different courses and different Q&A simultaneously. So what is the range of the cosine similarities? So when the cosine similarity is, it is varying between +1 and -1. Cosine similarity of 1 means the two vectors being compared are perfectly aligned in the same direction. So say for example, if I make a search engine, a very trivial search engine, and I have placed in it the vector representation, and I gave a statement which consists of say a few words, 3 words. So then what is going to happen is that the cosine of the vectors will be taken of the input with all the indexed results or the available results, and the matching will be this cosine value based upon they will be sorted, and the cosine value of 1 means that they are fully compatible or they are exact match. So it works like a search engine. So this is when they are similar, okay, which is so basically the quadrant you can say they're also the same. They are unrelated. The cosine similarity is like 0, and this is opposite of -1. So for the given table below, the attributes of father and mother, calculate the cosine similarity. So let me zoom this. So I have these features, okay, father and mother. So father is human, father is male, and father doesn't have long hair, and father can't cook, but there are many fathers who can actually cook also, and both are nouns and both are not verbs, and both are humans. So we have this vector representation of father, and we have a vector representation of mother, and when we do that, take the cosine similarity, so we see that 1 multiplied by 1, so we have, and of course then is the calculation which I've already mentioned. So we see that the father and mother similarity is 0.671. Okay, so that's how the cosine similarity is calculated, and of course that's how you can implement a simple search engine also. So let's move on, and why TF-IDF is used. Now I will go into more concrete details. So this is basically the example which I mentioned in the previous Q&A also. So identifies the important words in a document. Identifies the important documents. Why? Because of their occurrence. Reduces the influence of common words such as the stop words. So you don't need to remove the stop words. Of course, if you remove the stop words, the complexity of the problem reduces. Improves document retrieval and ranking because there is a concrete similarity measure. There are multiple of them. Feature representatives for machine learning, and of course handles large corpora efficiently. I'll explain to you how it handles large. TF-IDF scales well when dealing with large corpora, term frequency, document frequency separately. TF-IDF is computationally efficient and can handle massive datasets without requiring excessive resources. And TF-IDF helps in determining semantic similarity between the documents. Similarity, which was not in the case of the bag of words model, which was based upon the frequency count alone. So if we have this document, the cat is on the mat, the dog is in the yard, and so on. So we can do these calculations based upon these relationships, and you can see that the inverse document frequency of the cat is 3 over 2, log of 3 over 2. And the TF-IDF score for the cat is 0.176. So this way we can do all the calculations. And how to handle large vocabulary sparse vectors using this approach. So we do the word embedding. So what happens in word embeddings, that instead of having a single feature associated, we can have multiple features. Okay. So Word2Vec, these embeddings are much lower dimensional space, so they require, because it's a combination, but of course it requires human intervention, and of course since these words are combined, so it reduces the dimensions. And the feature hashing trick involves mapping the words in large vocabulary to fixed size vectors. So that still captures the relationships. Sub-word tokenization. Methods like byte pair encoding sentence break into smaller sub-word units. So we have sub-word tokens. So that basically reduces the complexity of the problem. And then we have the pre-trained language models, BERT, GPT, and Elmo, which helps in better performance. And so we can have topic modeling also. You can read this. It's not very complicated. So what are the major limitations of the vector space model? As a matter of fact, there are quite a few of those limitations. So not possible to go all of them in lots of details, but let's briefly look at them. There's no semantic understanding because we are looking at the vectors. And in the vectors we are not maintaining the order of the words. Sparsity and high dimensionality because the vocabulary can be very large. Loss of word order information, it is lost, but we are able to identify the important words. Inability to capture polysemy. How it is because for example, if you talk about the bank, this example I've given a number of times. So the bank can be a financial institution, the bank can be the bank of a river, but since there is no there is no word order information, so it's lost. What was the meaning of the word bank with the same spelling? and so this is an issue over here. So additional major limitations: inefficient in handling large corpora. Why? Because the vocabulary size increases. The result in increase in the dimensions. That results in increase in the space complexity. That results in the requirement of computational power. Synonyms cannot be handled, as mentioned before. Happy and joy are treated differently, increasing the complexity of the problem. And no support for complex queries like find articles on climate change and so on may not be matched if the terms climate change and renewable energy do not appear together. So if you are using unigram, this is gone. Okay. So and of course if you use if you use biograms, it has its own issues. So we end with the differences between bag of words model and the vector space model. So these are the this is the explanation of those differences. Okay. And if I could just zoom it here, so we'll go over this summary. Word representation: raw frequency counts, term frequency, inverse document frequency. So we look at the importance of the words. Handling of stop words: no special handling in the vector space model. They automatically get a very low weight and their importance goes down. Equal to the vocabulary the size, but with weighted dimensions. The vocabulary size is the same. Word order is ignored here. Word order is ignored in the vector space model, but the words with importance are highlighted. Handling of common words: all words are treated equally, all words are not treated equally in the vector space model. Use case: simpler models better suited for complex tasks like retrieval and clustering. Retrieval I mentioned, like a search engine. Similarity calculation just based upon the word count. Over here it's based upon the frequency and the importance of the words. So that is all I have for this topic, and I hope you would have found it very useful. So to make this understanding more concrete, let's look at an example and calculate the term frequency and the inverse document frequency for a very simple example. The cat is on the mat and the dog has the mat. Of course, it can be very complex also. So let's click on the answer. So we have these two documents written in front of you, and we start by tokenization. So every word becomes a token, is a unigram, and we calculate the term frequency. How many? So document 1 has 6 words, and the term frequency for each word is, say for example, the occurs twice, cat occurs once, and we calculate the term frequencies for document 1, calculate the term frequencies for document 2, and calculate the inverse document frequency, okay, which is total log of total number of documents divided by number of documents containing the word itself. So this we do it and we get a 0 here. This is for which? Document 1 and document 2. And we do this for the mat. Mat appears in both the documents, so 2 divided by 2 is 1, log of 1 is 0. And dog only appears in 1 document out of 2 documents, so 0.301. And then we calculate term frequency inverse document frequency by multiplying TF with IDF. So this is done for document 1. It's simple calculations. Term frequency multiplied by the inverse document frequency. In document 2, and we make this table. So we see that the has no value because it's a stop word. Cat has a value 0.05, and cat has a value, is has a value because it occurred only once. Mat has no value, occurred twice, and dog has a higher value 0.06 because in that document is was not occurring that frequently. So that's all we have for this. Of course, thank you very much.